Hey, welcome everyone. So we are here with Rahul, who is going to conclude the final session or the final talk for session 2. Rahul is also Rahul is at Jump Crypto, and he's specifically going to be talking about CycloneNTT here.
All right, thanks. Let me go to start. Hi, everybody. Yeah, I'm going to talk about kind of an umbrella, one of the components of like kind of an umbrella project that we've been working on called Cyclone, which is really targeted to for hardware acceleration of core primitives zero knowledge proof systems. So I'm going to give a bit of context first. So why are we doing ZK? First of all, at Jump Crypto, maybe you've heard of us, maybe you haven't. And then I'll go into kind of background material on FFTs and Cooley-Tukey, and then go over some of the algorithms that we used specifically in our implementation. And I also wanted to mention actually real quick that this is joint work between a bunch of folks at Jump, some of the hardware folks who are kind of on the Jump Classic side, and then some of the folks on the crypto side as well. So there's a couple of things that I wanted to mention. One is that we're truly like all in on scaling ZKs. We think we want to be sort of like the infrastructure builder, so we want to be like as close to the infrastructure as possible. So we've contributed to projects like Wormhole and Pith, which have been particularly useful on ecosystems like Solana, and now we're expanding to other ecosystems and chains. And we also want to be kind of building and contributing in the space in ZK because we really think it's going to be part of the core infrastructure of blockchains, and possibly also for Wormhole and Pith as infrastructure components. So we kind of took the approach that we wanted to kind of scale the lowest level primitives. So obviously there are a few things. There's elliptic curve operations at the bottom. There's finite field arithmetic, and then there's some of these other components that will go into multi-scalar multiplication, which a lot of folks have talked about, and then number-theoretic transforms, which we'll talk about today. And obviously there's other work, amazing work on like accelerating finite field friendly hash functions, and also building these hash functions in a way that's amenable to these proof systems. Okay, so let's go over some of the background for this. So the first thing that we're going to go over is just the basics. What is a discrete Fourier transform? So there's kind of two components to a DFT. There's the twiddles, which are kind of roots of unity in your field. And then there's these coefficients that you actually want to transform. So you want to take X and you want to transform it some vector values, and you want to transform it to another vector of values, Y. And so if you take the naive approach of computing a DFT, you're going to get this pretty bad complexity. It's like quadratic complexity in the size of the DFT that you want to do. And that's potentially very, very bad for your application. So obviously there's been a ton of work, over the last like half century to improve this. And one of them, kind of the main sort of algorithm that has become famous is the FFT, or the Fast-Fourier-Transform. And so the idea that was proposed by Cooley and Tukey in 1965 was really to like factorize your problem into a smaller component. So factorize your n into n1 and n2, and then recursively evaluate that FFT on n1 and n2. And so you can see that like the complexity is reduced. So if you set n to be a power of 2, then you get n log n sort of order complexity, and that's really kind of the asymptotic improvement that you get in the long run. And that was largely responsible for a variety of things. Obviously like the birth of digital signal processing likely would not have been possible without FFTs. So there's two main components to this that we kind of want to target. One is like the evaluation, and then the other one is like the memory access. So how do we actually access these twiddles if we're trying to do really, really large instances of FFTs like we need to do in these proof systems? So there's two common ways to compute an FFT. One of them is called decimation in time, and the other one is decimation in frequency. And so they're basically just ways to read the input. One of them is the inputs are in bit reversed order, and then the other one, like the frequency outputs, are actually in bit reversed order, and they're equivalent, but there's sort of, you might want to use one approach in different situations. So you kind of have to make these choices when you're thinking about optimizing FFTs. Yeah, and then there's the butterfly computations, which we'll also go over in a second. Yeah, so butterflies are basically these operations that you need within an FFT. So basically combinations of the smaller factorized DFTs that we just talked about with those twiddle factors, which are those powers of omega that are in the field. So here's an example of the diagram here is like basically an example of a butterfly network or like an FFT network. You can see that the inputs are going to be put in on the left and you're going to get the outputs on the right. And then these operations that you see with like these arrows are actually the butterfly operations. And so, you know, people have different notations and different ways of expressing this, but in this usually, you know, the up arrow is really like the addition. So you take the two inputs, you add them together, and then you multiply by some twiddle factor. The downward arrow is representing, you know, kind of where you're going to apply the twiddle again, and then how you're going to do the computation. So that might be like the two, subtracting the two inputs. And so you can see an example of like a diff butterfly here with the mathematical notation, which is just adding two inputs and getting, if you take the left input and the right input and you add it together, you get the left output. And then if you subtract the two inputs and you multiply by a twiddle factor, you get the right output. And so, which are basically the odd indices. Okay, so let's go over what's the kind of architecture that we use for CycloneNTT at a very, very high level. So we had four main things. We had, you know, external memory for in DRAM or DDR. And the reason you need external memory here is because we really can't fit this many values and twiddle factors on chip, like on the FPGA, because we're doing instances of like, you know, 2 to the 24, 2 to the 21, 2 to the 28 potentially. So it really, we can't fit these things on chip. And then we have a set of large FIFOs that are expressed like as ring buffers, which I'll go into more detail, but some part of it's on chip and then some part of it's off chip as well. And so, and then we have this NTT like submodule on chip that's actually doing the evaluation of the NTT. And then we have data access to the host or the CPU through the PCIe. Okay, so how do we actually do this? I just want to give like a brief overview of what the architecture looks like, and then we'll dig into each component of this and try to see like what we can actually optimize. So the initialization step is really to pre-compute all the twiddles. So we take all the twiddles that we need to compute, and we just pre-compute them, and then we sort them in bit reverse order. So that's for the decimation and time factorization that we talked about before. And then we send those values to the FPGA over the PCIe bus, and then we receive them in bit reverse order. So the basic idea of the Cyclone component of this, the reason we actually called it Cyclone, is we want to load the twiddles in, and then and the values from the FIFOs that we have in external memory. And we want to process those twiddles and values in the sub NTT module, and then we want to push them back to the FIFOs and back into external memory. And so you can see like there's some sort of like there's a loop here, and so just as a pithy name, sort of we called it Cyclone. And then we want to receive the values or send the values to the host over PCIe after we've computed them. Okay, so what is the sort of like main algorithmic optimization that we made? So there was a paper that was published a few years back by Kevin Bowers and some other folks. Kevin Bowers happens to be the chief scientist at Jump as well, and so we had a lot of his input on this. He essentially found a way to use a decimation in time factorization with a decimation in frequency butterfly for the inner loop. And so that allows you to essentially reduce the number of twiddle accesses from n log n to O of n, and this is pretty substantial. I mean, this is a asymptotic improvement by logarithmic factor in your actual memory access, and it's not very well known, but it happens to be extremely useful for cases in which you have large instances of n, and you do it in these proof systems. And so obviously we're doing these things over the Goldilocks field, which we'll talk about a bit, but I want to focus mainly on the architecture because this can be adapted to other fields as well. All right. So there's basically, the basic primitive that we're actually looking at here is single layer streaming. So what does this mean? So I went back, I showed a diagram of what the FFT network looks like. And so we want to process each one of the layers of the NTT network at a time. And so within each layer, we can parallelize because we're actually pipelining these operations through the NTT module on the FPGA. But then we need to figure out a way to actually stream the twiddles in so that we don't have like random access for the twiddles while we're trying to compute these entities. And so you notice like, in that diagram, the number of twiddles that you actually need to access are cut by half at each layer. And so these, again, these inter sort of layer computations are sequential, but the intralayer are parallelizable. But still, even with this, even with a way to like actually stream the twiddles in and make sure that the twiddles that you're receiving are ordered in the correct way, you're still memory bound. And so the goal of this is to kind of take a memory-bound algorithm, a traditionally memory-bound algorithm like the FFT or the NTT, and make it a compute-bound algorithm by using some techniques, streaming techniques, essentially. So how do we do this? We kind of use like a 2 FIFO architecture. So basically, each butterfly operation feeds into the next layer, right? So like at each layer, we have sequential operations, and so we need to set up like these FIFOs to manage the inputs and outputs. Something I put off here, but that's okay. So the FIFOs are managed off chip in DDR, and there's some addressing that you do on chip as well to make sure that you can actually access these FIFOs efficiently. But I won't go into too much detail on that. Yeah, so let me go into a bit more detail on what this 2 FIFO architecture looks like. So the diagram on the right kind of demonstrates a really, really simple example with like a size 8 NTT. So you can imagine like you have the values indexed from 0 to 7, and you kind of want to, after you kind of recursively break down these inputs, you notice that you have like 0 and 4, 2 and 6, 1 and 5, and 3 and 7. Those indices are the pairs that you're feeding into the butterfly network. And you're, instead of like computing the butterfly and then just pushing it into a single queue or a single FIFO, what you're doing is like effectively ping-ponging between these FIFOs. So once you compute, you put the index 0 into the left FIFO, you put 4 into the right FIFO, you compute the butterfly, and then you put both of them into the left FIFO. And so at each layer, the number of times you ping-pong between the FIFOs actually decreases by half. And so that's the idea, is that you want to basically create a way for you to actually stream these operations in, so you can feed the previous layer's output into the next layer's inputs. And you can notice like there's indices that you have to manage. So the target butterflies are actually 2 to the L rows apart for each layer, where L is like the layer. And then this so kind of punchline is that this 2 FIFO architecture enables quick and easy memory access that we need for streaming. And you can actually extend this idea a bit further. So imagine instead of processing each layer at a time, you decide, okay, I'm going to start processing like multiple layers at a time. So I can process maybe 3, 6, 8 layers at a time. And so what you need to do is just require, the change that you need to make is have more FIFOs to manage this. So, and the number of FIFOs has to be, a multiple of 2. Okay, so what are some additional items? So these are kind of more hardware specific things. So, if you look at the output buffer analysis for the egress FIFO, so I'm talking about like after you're ingesting the values on the FIFOs, you need to actually, put them in the FIFOs back so they can go back into external memory. And so you'll notice that like the egress FIFO switches, every 2 to the L, or 2 to the, if you have in a multi-layer architecture, it's 2B to the L beats. So it's ping-ponging between these FIFOs. But the problem is, like once at each layer, you're using fewer and fewer FIFOs, so everything just gets merged into the left FIFO here. If you can see on the right, like everything just gets merged into the left FIFO, and so the egress FIFO just needs to keep waiting. It's like it's asking like, what's happening here? Like nothing's getting loaded into this. We need to wait for the inputs to actually get processed, and so we need some like additional things to make sure that this is as fast as possible. And so this is like an architecture called quasi-streaming. I won't get into too much detail, but the idea is that if you can sort of order the inputs in a way such that you're ping-ponging as much as possible between the FIFOs, even though you're going to the next layer and going to the next layer, then you can basically ensure that the buffer that you're managing on chip is as small as possible. Because if we didn't have this, then the buffer would grow kind of arbitrarily. And at the end, at the end of at the last layer, you'd have like big N over 2 outputs that you'd have to manage. So before they're like processed into the egress FIFO. Okay, let's see what else. So I'll just go over the results quickly. So this is just a brief sort of diagram. This is in microseconds. And so the punchline here is that the multi-layer streaming architecture is definitely better for latency, but there's some other things that we kind of analyze as well, including power utilization, and it seems to be that the 3-layer approach is probably the best in terms of the latency and power trade-off. All right, that's all I have. Thank you.
All right, thank you, Rahul. So let's leave a few minutes for questions. If anyone has any questions, feel free to leave them either in the comments section or the QA section. We've already got a few here that are pushing up on the Q&A section, so I'll go ahead and just pass them off to you, Rahul. First is, you mentioned streaming as a technique for converting memory-bound to compute-bound algorithms. How much improvement can we achieve by doing this conversion in principle?
Yeah, I think it's hard to say like what you can get in principle, but the idea is that instead of relying on, like if you have sort of the latency latency improvement that you're gonna get is basically based on how much you can compute at a time. So like instead of being memory-bound algorithms when you compute out, it's gonna be a compute-bound algorithm. So like we're just converting between like the design space, right? Like we're just moving the design space or the trade-off space a bit, but it doesn't really, like it sort of changes the perspective you have on the problem. So if it's a compute-bound algorithm now, then the goal for you is to like optimize, like what multipliers are on the chip, like what can you do in terms of computing things as fast as possible, and that kind of becomes a more like HPC sort of problem as opposed to a how can I manage external memory. And so the next thing is sort of what's the bandwidth for transferring these values from external memory to on chip, and so that becomes another bound that you have to think about. I think for FPGAs in particular, and the one that we used, sort of that bandwidth was pretty limited because it was using like I think PCIe 2 in this case, which is pretty limited. So it's like 2.5 gigabits per second, which is not great, at least in this environment.
All right, thank you. And then one more question. What's next for Jump in the direction of ZK hardware?
Yeah, I think we're open to things. I think what we want to do, in general, is like be partners in the space and sort of build core infrastructure that can help the ecosystem move forward. And so we're always interested in projects. Obviously there's a few folks on here who have done some work on ZK hardware, working on compilers. Like we sort of our goal is to really help this ecosystem move forward, and we have resources internally as well that have spent many years in this environment. So I'll just mention like there are some other cryptographic hardware acceleration stuff that's going on at Jump as well. Is the FireDancer project, which is sort of dedicated to building a second validator client for Solana. And so a lot of the sort of core optimization techniques that we've built in-house over like 20 plus years of trading in HPC environments have become sort of very useful in blockchains. And I think that will probably be the next sort of direction we want to pursue.
Awesome. Thank you very much, Rahul, and thank you very much for your presentation. And so for now, what we're going to do is we're going to go into the final break session. And in this final break session, I'm going to have one more question contest for the audience. And again, fun little activity for everyone to kind of freshen up